Welcome back to Chemistry Notes Part 4. As I mentioned in the first several parts, is we're going to keep these notes simple. We're going to keep them short. I like to keep this video right around 10 minutes, 11 minutes, 12 minutes. Obviously, if we were doing this in class, we probably could cover parts 1 and 2 in one day, parts 3 and 4 in another day. But I want to break it into small chunks because if you're doing this at home, I want to give you plenty of opportunities to ask questions before you move on. So the first thing we're going to talk about today is chemical bonds. And a chemical bond forms between atoms when valence electrons move between them. Now here's the neat thing. We're going to talk about this in 2 different days. These bonds can either be transferred or they can actually be shared. So when we look at this, we're actually going to break this into 2 separate days. We're going to talk about the transferring one day, and we're going to talk about the sharing another day, because this can get a little bit complicated. So we're actually going to take 2 different days to talk about both of these concepts. So what is a chemical formula? This is something you see all the time. Very rarely in nature do you see a element all by itself. You don't normally see hydrogen all by itself. And I know some of you are saying, well, what about oxygen? You know, my grandma has an oxygen tank. And so that's all by itself. Well, not really. Oxygen usually is combined with itself. It's a diatomic molecule. It's O2. If you put 3 oxygens together, it's actually O3, and it's called ozone. We'll be talking about that later in the year. So a chemical formula is a shorthand way of showing the number and the type of atoms in a compound or a molecule. And here's an example. What you see right here, this is methane. You see these models here, you know this is the carbon, you know this is the hydrogens. Here's the K shell for carbon. Carbon is number 6. So it's going to have 6 electrons, right? So there's 1, there's 2, 3, 4, 5, 6. Now each hydrogen has 1 right here. We'll say it's those. But this shell can hold as many as 2. This one can have as many as 8. And you notice if you count both of them, because they're actually showing them right now, there would actually be 8 in that shell. Now, here's the shorthand way of saying it. Instead of writing it all out, or instead of saying, writing out carbon, we just use the symbols. The large C stands for carbon, the large H stands for hydrogen. And this subscript right here, this is the number of hydrogen because it's right next to the hydrogen. Now one thing I didn't mention before, when you're working with the periodic table, the first letter is always capitalized in the symbol. The second letter must be lowercase. And there's a really good example of this. If I write SI, what is this? Some people may look at the S and I and say, oh, I know. If I look at the periodic table, number 14 is silicon, right? Si. Well, silicon is actually large S, small I. Okay, and that's pretty important to know. Large S, large I is actually sulfur and iodine. So, one that's really, really similar to this is nickel. Nickel is Ni. But if we put large N, large I, it's nickel and iodine. So make sure you always have small letters for the second one. And so because this one right here is large, we know it's not a small h, it's a large H, so it's hydrogen. Now if you ever have a large number in front of the whole molecule, what that means is that it's CH4 and there's 2 of them. So you'd have 2 full molecules of it. Where the 4 down here just means there's 4 hydrogens. So if you count those, 1, 2, 3, 4. Now one type of bonding is called ionic bonding. And ionic bonding is the giving up of an electron. And this often forms between metals and nonmetals. So let's take a look at an example. We have sodium, and sodium you can see is the Na, so that's why sometimes it's nice to know what the symbols are. And if you know that Na is sodium, you don't have to look up the board. I can call it sodium versus some people just say, oh, it's Na. Well, that's sodium. And then you have your Cl is chlorine. Notice it's a lowercase l. It's not a large L, so it's not carbon and iodine. It's chlorine. Now, if we were to take a look at the Bohr model of a sodium, if I take a look at sodium, if you find Na on the periodic table, it's number 11. So sodium on the first shelf, if I drew in a shell here, it would have 2 electrons, because then it's full. That's the K. If we drew the next shell around here, it would actually have 8. Now, so far, if you've been counting the X's, there's actually 10 of them, but it's number 11. So if I draw on that last one here, and that's because it's on the outer shell, that's your valence electron. So that's why sodium only has 1 electron in this ring. Now if we look at chlorine, we could do the same thing with chlorine. We could draw it out. I'm not going to do it here, but you could draw on your different shells. And you would find that on the outer shell, it would have, what, 1, 2, 3, 4, 5, 6, 7. Now, in order to be full, both of these would need 8. So they're both not full. And what I mean by full is they would have a full outer shell, or what they would be considered to be full. And when elements have full outer shells, they're balanced, they're stable. So what do we have here? If we have chlorine, chlorine needs to get 1 more. But sodium would actually need 7 more. Or what we could do is we could transfer. If sodium were to give chlorine 1 of its electrons, the chlorine would have 1 more, which is what it needs. And by getting rid of this, we go back to, we get rid of this shell right here, and we get back to the L shell, which is full. So that's what we mean by the sharing, or the giving up of electrons. So this is an ionic bond. An ionic bond, again, is the giving up of electrons. So here we see sodium chloride. Now you see something different here. Here's a plus and a negative. Remember, sodium gave up an electron. And because an electron have a negative charge, there's actually 1 more proton here. That's why, and protons have a positive charge. That's why sodium would be the positive end of this molecule, and chlorine, it's why it shows up as being negative. So when we look at this, I like this cartoon. Perhaps one of you gentlemen would mind telling me just what it is outside the window that you find so attractive. And when you look at these, you can see these right here have the negatives, and these right here have the positives. So remember, just like any magnet, you got your positive and your negative, and you've always learned that opposites attract. They do here with magnets. So that's why when we look at this Lewis structure right here, that's why the Lewis dot structure is so nice, because we know that oxygen, we work with oxygen in part 3, it needs 2 more to be full. So when we take a look at that, let's go back once. When we take a look at this, you know somewhere it's got to pick up 2 more electrons to be full. 2 more electrons to be full or stable. So let's talk about an ion. What is an ion? An ion is a charged atom or molecule. It is charged because the number of electrons do not equal the number of protons in the atoms or molecule. So we just saw that happen with sodium chloride. Sodium became positive and chlorine became negative. Now, when an atom is attracted to another atom because it has an unequal number of electrons and protons, the atom is called an ion. If the atom has more electrons than protons, it's a negative ion. Sometimes they call this an anion. And if it has more positives than electrons, it's called a positive ion. So in the sodium chloride, because the sodium chloride, if you remember here, the sodium was your positive. So this would be your positive ion, or sometimes called a cation. And your chlorine here was your negative. So this would be called your negative ion, or sometimes it would be called an anion. So here we can see this example right here, they're even. The number of electrons equals the number of protons, so it's neutral. It's not an ion at all. Here, the atom is negatively charged. It's got one more electron, where this one has got one more proton, so it's positively charged. And you can see this down here, 5 protons versus 6 electrons. That's why it has one more electrons, and it's a negatively charged one. This one is positively charged because it has one more proton than it has electrons. Now, before we leave this part, let's quickly talk about metals. Metals are most elements. If you looked at a periodic table, most elements on a periodic table are considered to be metals. In fact, about 75% of the elements are considered to be metals. What do we know about metals? They're hard, they're shiny, they're malleable. Malleable means they can be shaped, they can be bent. Like you can shape them into pots and pans and jewelry and wire. They conduct heat and electricity well. That's why pots and pans are usually metal. Wire conducts electricity, which is really good. And typically they have 3 or less electrons in the outer ring. In other words, they have 3 or less valence electrons. Nonmetals are gases or brittle. They're dull, they're insulators, and they typically have 5 or more electrons in the outer ring. In other words, they're the opposites of a metal. And then you have your metalloids. These have properties of both metals and nonmetals, and they form a stair-step line on a periodic table. So here we can see the metalloids are right here. So that's a metalloid, this is a metalloid. Notice there's a few examples that aren't considered to be metalloids on that stair-step pattern. Now you might ask, why are we talking about metals, nonmetals, and metalloids? Because once we talk about bonding, a lot of times, whether it's an ionic bond or covalent bond, they're going to combine with certain elements. So metals won't always combine with metals, nonmetals won't always combine with other nonmetals. It really depends on what type of bond it is, whether they're going to give up its electrons or it's just simply going to share electrons. But we'll learn more about that in part 5 of your notes. As always, if you have any questions about these notes, just ask your teacher. Thanks. Bye.